All right, guys, we're going to pick up where we left off on Monday's lecture. This is the section on mass spectrometry. So, this is another analytical technique that allows us to learn something about a sample. As the name implies, with mass in the title, the major thing that we learn from mass spectrometry is something that seems pretty simple on the surface, but we actually can learn something about the molecular weight of a compound. If we use a particularly sensitive style of mass spectrometry called high resolution mass spec, we can actually measure molecular weight out to 4 decimal places, which will actually give us the ability to convert that molecular weight into a condensed molecular formula. So we can actually tell exactly how many carbons, hydrogens, oxygens, etc. are in a molecule based on a high-res mass measurement. When we take a look at the mass spectra that you get from a normal mass spectrometry experiment, we'll see some other information that we can learn. So we can actually learn a little bit of structural information or connectivity, basically how the atoms are arranged. So we can learn a little bit about connectivity based on this topic called fragmentation. So what we will find is that the experiment that we do for mass spectrometry imparts so much energy on the sample that not only do we get some information about the total molecular weight of a molecule, it puts so much energy into the molecule that some portion of it will fragment into other pieces, which we can also detect. And based on those pieces that we detect, we can kind of put them together to learn a little bit about how the molecule is connected. So those will be the things that we'll look out for in this section of learning how to do. So in very briefly, we're going to talk about how the experiment works. And it's a pretty simple process. It's akin to throwing a piano off of a roof and then trying to put it back together to figure out what it was that you just threw off the roof. So here's how the whole process goes. We basically take a sample of the analyte that you're interested in, we vaporize it. So this is a gas phase experiment typically. And so once it's vaporized, it goes into a gas chromatograph, which then feeds into the mass spec instrument. And so when it enters the mass spec instrument, what ends up happening is we ionize the sample by removing a single electron from it. And so what we end up doing is we take the neutral molecule that's in the vapor phase, we hit it with a very high energy electron beam. And as that electron beam collides with the molecule, what ends up happening is it will eject a single electron from the molecule, and it will leave behind a positive charge where that electron used to be. And so what we will end up getting is what's called the molecular ion, which is the molecule that we're interested in minus just a single electron, right? And you guys know electrons have a very small mass. And so this is essentially a charged version of the whole molecule. Since the only thing that's missing from that is a single electron, it weighs essentially the same as the neutral molecule. So when we measure that radical cation that's formed, when that hits the detector, we can actually measure how much that piece weighs, and that gives us the molecular mass. And so this is actually what gets measured in the mass spec. We actually measure the formation of these positively charged radical cations. Now, the thing that you have to think about here is that when we shoot this high energy electron beam at the molecule, we're putting in a tremendous amount of kinetic energy. And so just as a simple comparison, the average carbon-carbon single bond in an organic molecule has about 85 kilocalories per mole. That's how much energy it takes to break that bond. If you compare that to how much energy we're putting in with the electron beam, 16,000 or so kilocalories per mole. So this is a very high energy experiment. And so what ends up happening is that the ionization event imparts a tremendous amount of energy into the molecule, which can cause it to further break apart into fragments. So ionization can also cause fragments. And if the fragments are positively charged, we can measure those too also. So we get not only the molecular ion, which by far and away is the most important thing that we learned from the mass spec experiment that gives us the molecular weight, but we can also see these fragments that are charged, and that can tell us a little bit about the structure of the molecule. And so here's a little bit of another slide that talks about that. So again, the big thing to take note of is that when we use the ionization event, it puts so much kinetic energy into the system that not only do we get this molecular ion, but sometimes as a way of it giving off energy, it can fragment into smaller pieces. And we get two types of fragments. We get positively charged fragments, which we can measure, and then we will also get fragments that are neutral compounds, so either totally stable molecules or fragment radicals. But the thing to remember is that what we're measuring here are charged species. So really the only positively charged species, the only thing we can detect in this experiment are the pieces that are positively charged. And so what we will get out of this is we'll get the molecular ion, which is the part that we really care about. That tells us, again, molecular weight. But we will also be able to see peaks corresponding to those fragments, which will tell us a little bit about connectivity, if we can piece together what those smaller fragments are coming from. Okay, so that's sort of the series of events that we're going to be looking at in this experiment. All right, so this is a schematic of one type of mass spectrometer. It's a simplified one, but this will give us an idea of the important things that are happening. And so again, we're going to start over here on the left-hand side with the neutral molecules that are in a vapor. Okay, those are going to pass into a chamber that is indicated here. So what we have is we're going to have a filament here that gets super duper hot, and what ends up happening when that filament gets hot is that's where the electron beam comes through perpendicular to the sample, right? And so we also have these things like these repeller plates to keep things moving in the right direction. So we have a positive plate in the back to keep the ions from going back into the vaporizer. And then we have these things that are called accelerators, these negatively charged plates that are there to accelerate the positively charged cations that we make from the collision of the sample with the electron beam that's coming out of that filament. Okay? And so what ends up happening is we generate charged vapors in this chamber, we accelerate them into a vacuum tube, and so then everything comes out of here into the vacuum tube. Okay? And so what ends up happening then is that we have a vacuum pump here that can pull off any neutral molecules or fragments that aren't charged. And then only the positive ions come through there. And what ends up happening is we have this magnet that can pull on the positive charges, and we sweep the magnetic field. And by sweeping the magnetic field, what we can do is we can sort of change the trajectory of those positively charged particles based on their mass. And so what will end up happening is that some of the ones that aren't appropriately selected at that magnetic field will miss the ion exit slit, which sits here. And so as we sweep the magnetic field, we can slowly scan from high to low mass so that only the molecule, so that only the part that we really care about, that one particular molecule that is the right weight and charge, will pass through and hit the detector, and we get this plot at the end of the day that has a number of peaks on it. And so we'll know the mass of each of those peaks by this experiment. A couple of important things to take note of. Again, we've mentioned this already, but only positively charged things are detected. Okay, and then the readout that we get on the spectrum is a mass to charge ratio, M over Z. Okay, so this is important. This is actually the number that we're getting. It's a mass over charge ratio. In these types of experiments, since we're only ejecting a single electron from the compound, the charge is always going to be +1. So really what that means is if you take that mass to charge ratio, if you're dividing by 1 always, you have mass over 1, which is equal to mass of the compound. Okay, and so in this way we can actually figure out how much the molecule weighs just by ejecting one electron, accelerating it through this system until it hits the detector. And then that's sort of what we get out of these reactions, out of these measurements. And so this is an example of what a mass spectrum looks like. Okay, and so there's a couple of things to pay attention to here. So the y-axis is always going to be relative abundance. And so really basically what this is a percentage scale, right? So 0% down at the bottom, 100% at the top. Okay, so what you can take for that is that the peak that comes all the way to the top, which we call the base peak here, that's going to be the most commonly encountered ion in the measurement. So this is the most common ion that was detected. Okay, but what you'll notice is that doesn't come all the way down to the end of the mass to charge ratio that we see on the x-axis. So the x-axis is always that mass to charge ratio, which, remember, since the charge is always 1, this is really the mass of the fragment that's hitting the detector. Okay, and so if I take a look here at the mass spectrum of pentane, so this is pentane. If you were to add up the number of carbons and hydrogens from the periodic table, you would see that this compound is about 72 grams per mole. Okay, and so what ends up happening in this case, when I actually take that molecule and I hit it with a high energy electron beam, somewhere on that molecule, one of those CH or CC bonds is going to lose one of its electrons. And so what I will get out of that is pentane minus 1 electron. So I have a positive charge and I have a radical, an unpaired electron somewhere in that system. So basically what that means is one of these bonds somewhere in the molecule is going to be missing an electron. But since an electron weighs almost nothing, this positively charged fragment weighs the same in terms of its mass to charge ratio as the neutral molecule. And so that's what we end up detecting here at 72 mass units, is the molecular ion of this compound. Okay, and so what ends up happening with these other peaks that we see here is we have the loss of pieces that correspond to again, that situation where we have imparted so much energy into this system that that molecular ion has enough energy to fragment. And so what you can see here in the this case with M minus 15, that's going to be a common peak that you'll see with a lot of organic compounds. What this is basically is the molecular ion after having lost a CH3 group. So we've had so much energy imparted into this system that a CH3 group falls off of this molecule, lose those 15 mass units such that we end up getting, in this case, a butyl cation. So what we've detected in this spot is a butyl cation that weighs 57 mass units because we've split off and lost that, that methyl group. The base peak, the most commonly encountered peak in this system, actually turns out to be the loss of an ethyl group. And so M minus 29, that means we've split off an ethyl group from this system. And what we're detecting in its place is that propyl group that's left over. Okay. And then you can parse out a couple of these other peaks. Some of them are more or less easily assigned. This 15 mass units, this is actually a positively charged methyl group that has flown down and hit the detector. So when this thing breaks apart, it split off a methyl group at one point. Same thing with this 29 mass unit. That actually turns out to be a positively charged ethyl group. So remember, these things that are positively charged, these are the things that we're detecting. And so the things that we're actually seeing in the experiment, we're seeing an ethyl, a methyl. We see this propyl group here, and then we also see this butyl group here. The major thing that we care about here is this molecular ion, the entire molecule minus one electron, which tells us the mass of the compound. Okay, and so that's sort of what these types of experiments look like. So let's continue and look at another one. So actually, we're going to take a quick look at sort of explaining where we see these peaks and their intensity. So what we're going to talk about next is sort of what controls the relative abundance of particular fragments. So let's take another look at this same mass spectrum. Actually, no. So this is the one that we're looking at. So let's take a look at that base peak. So again, the reason that base peak is there is we've lost an ethyl group to make a butyl group as a positive charge, right? But what governs the intensity here is the nature of that cation. So this is a primary cation. So that's actually the peak here that corresponds to 57 actually. So that's a really quite small peak here. Okay, so let's see what will happen if we stabilize that carbocation and lead it to a more stable carbocation. We should see that base peak. We should see that peak grow. So what we're going to look at now is a constitutional isomer of pentane. So let's look at this one. This is 2-methylbutane. So this actually has the same molecular weight. But what you can see is if you look at this mass spectrum, we see the same peaks, right? We see 72, we see 57, and we see 43. But what you can see if you compare that mass spectrum that we were just looking at, that 57 peak is quite small in the linear pentane, but it's gotten much bigger in the 2-methylbutane. And so what is the reason for that? The reason is that by losing that methyl group, so again, this molecule still weighs 72 grams per mole. So we should expect to see the same exact molecular ion peak out of this system. And so that's what we see. So again, this is the molecular ion. That's the molecular weight of the compound. But the thing I want to clue in on again is this peak at 57. It's much larger here, happens much more frequently than it did in this case. And so the reason for that is that in this case, the 57 peak after we lose a methyl group is quite small because we're forming a primary carbocation. If I look at this case, if I think about splitting off a methyl group here, right? If I pull this methyl group off and lose it, what I get in this case is a carbocation that's going to weigh the same thing as the last one, but it's a more stable carbocation, right? So in this case, we actually have a secondary carbocation that's more stable, so then that methyl fragmentation will happen more frequently, right? And so that's going to correspond to a higher intensity of that peak as compared to the other one. We still seem to see the 43 peak as the base peak in this case, right? So again, this is the base peak because it's the most abundant one. And we can rationalize that that one should also be quite a stable peak. That's again the loss of a ethyl group. So if I pop off this ethyl group, what I'll get is a mass unit here of 43 that corresponds again to a secondary carbocation. So that's quite stable, and so that's why we see those two peaks being the major fragmentation peaks. All right, so let's move on a little bit and have a look at some other stuff. So this is again what's happening in this case. It's leading to that mass to charge ratio 57 peak. So the molecular ion gets hit with a beam of high energy electrons. Somewhere on this molecule we eject a single electron. We actually make a positively charged species because of that. And then what ends up happening next is we actually fragment off a methyl piece. So basically what we end up losing here is a methyl radical. We lose a neutral methyl radical. That gets rid of the radical that we have on the radical cation, but it leaves behind this positively charged species that is a secondary carbocation. So that's a stable species that flies down to the detector and hits the detector. Okay? Now, we have oversimplified things just a little bit. What we need to think about now is what are called isotopes. You guys know about isotopes, right? So different atoms have a varying number of neutrons on them, which changes their weight, right? Because neutrons have a mass. And what's unique about mass spectrometry is that it's every single charged molecule that hits the detector shows up in this experiment. And so actually, if we're quantifying individual molecules in this case, what ends up happening is that every now and then we're going to have a molecule that contains a heavy isotope of a particular atom. So when we look at these spectra, we see that mass to charge ratio at 72 AMUs. That's the molecular ion, right? And that's what corresponds to the molecular weight of this compound. But what we're assuming there, what we're seeing there when we have that molecular ion hit the detector is that all five of those carbons in pentane have carbon-12 isotopes. So we don't have any heavy isotopes of carbon in this sample. And so when that one ionizes, it runs down and hits the detector. Since all of these are C12 isotopes, we see a 72 AMU measurement that corresponds to 72 grams per mole, which is what you would get for the molecular weight if you calculate the molecular weight where all of the atoms are carbon-12. But what you guys may recall is that carbon-13 is about, I think it's about 1% abundant. And so what we see in that case is that we see occasionally a measurement where we've generated an ion where one of these carbons in there has the heavy 13 isotope in there. So that effectively increases the molecular weight of that single molecule by 1 atomic mass unit. And so every now and then, one of these C13s will be in the system, and we'll actually see a mass to charge ratio where we see a higher peak. And so if we look carefully at the mass spectra that we just talked about, we should see a peak, a small peak, right? Because we only have 1% abundant carbon-13, so it doesn't happen very often, but we should see occasionally an M+1 peak that corresponds to one or two molecules that have a heavy isotope of carbon-13 hitting the detector. So if we scan back up here at these peaks, we can actually pick out a tiny little peak, 1 mass unit above 72, that correspond to that M+1 peak. And so again, that's because of carbon-13 being present in that sample. All right, so if I scroll back up here and look again on that first one, I also still see that tiny little peak there, which corresponds to the M+1 peak. Okay, again, that's coming from carbon-13. And so with carbon, those M+1 peaks are very small because there's not a huge abundance of heavy isotopes of carbon. So what's the point of this? The point is that there are some molecules, like halogens, that actually have very large M+1 peaks. Because remember, the two different isotopes that we have for chlorine, so that's chlorine 35 and chlorine 37, those happen in about a 3-to-1 ratio, right? And so now we have a significant amount of that heavy isotope. And for bromine, it's even more pronounced because the two isotopes of bromine are present in a 1-to-1 ratio. And so in this case, you'll actually see what are called diagnostic M+2 peaks, right? Because in these cases, we can actually tell right away that we have chlorine and bromine in the molecule because we see multiple molecular ions. And so we'll see an example of that in just a second. And so you can tell where this will become most common, right? So again, the reason we don't see so much of that M+1 peak with carbon is because there's only about 1% of all carbon on Earth that is the 13 isotope. We never see an M+1 corresponding to hydrogen because deuterium is almost never encountered, right, in these compounds. So 0.01% of all hydrogen is a deuterium. Now, the places, again, where it becomes really important here are bromine and chlorine, right? So if you look at bromine, chlorine 35 is about 75% of all chlorine, and chlorine 37 is about 24% of all chlorine. And so in those cases, when we look at a molecular ion, we'll see M, and then 2 mass units later in about a 3-to-1 ratio, we'll see an M+2 peak. It's even more pronounced with bromine, right? Bromine 79 and bromine 81 are about equally abundant, right? So this is about 50% of each. And so if you have bromine in your sample, you'll see a 1-to-1 ratio. You'll see M, and then you'll see another peak right behind it equally as tall at M+2. And again, that's because about half of your sample has bromine 79 and about half of your sample has bromine 81. So let's have a look at what that how that shows up. I do want to pause here, though, and take a look at high-res mass in just one brief slide. So again, because these instruments are so sensitive that they can actually detect isotopes, we can make use of this in a productive way using a technique called high-resolution mass spectrometry. So this is a special mass spec instrument that can determine molecular formula of molecules because it can measure all the way down to 0.0001 atomic mass units. So as a quick example here, if I look at this alkane, this compound with 2 nitrogens, and this compound with 2 oxygens, if you go to the periodic table and compute their mass, they're all going to come out to 122 mass units. So the question is, how can I distinguish between these 3 condensed molecular formulas? Well, if I do a high-res mass experiment, I can actually get the mass all the way out to 4 decimal places, and I can actually see that at 4 decimal places there's a difference between these compounds, right? So they don't add up exactly to 122. They have these decimal places, and actually I can compute from that 4 decimal place molecular weight, I can actually get the machine to spit out the molecular formula for each of these things. So this can be a really useful technique if you have an unknown compound, because then you can put it in the high-res mass analyzer. It'll give you what the condensed molecular formula is, and then you know what you're looking for moving forward. All right, so that's high-res mass. Let's return to this isotopic abundance issue and look at a couple of examples where we can see these types of peaks show up. So here's a good example. If I look at propyl bromide, right? So propyl bromide has a bromine in there, and so what we're going to see is we'll see 2 molecular ion peaks, right? So if you were to go in there and calculate this mass for this compound using the periodic table, it'd come out to 123. But what you can see here is since we have 50% bromine 81 and about 50% bromine 79, you get 2 molecular ion peaks. So this particular molecular ion peak is coming from half of that sample, which is the propyl bromide where the bromine is the 79 isotope, and then about half of my sample is coming from the material where that bromine is the bromine 81. Okay. But what ends up happening is that once we impart these molecular ions with enough energy, we can actually see a fragmentation to the base peak where we have lost a bromine. In this case, we lose the bromine to generate a propyl carbocation. Which gives us 43 mass units. Okay, and so we can learn a great deal about these compounds just by looking at the mass spec. So the big clue here, though, is this 1-to-1 M plus 2. If I didn't know anything else about this molecule, I would know immediately that there's bromine there. Okay, so that's the big thing to conclude from that series of peaks where the things are doubled. Now you can see the exact same thing with chlorine. Right? So if you look at chlorine, now we actually have an M and an M plus 2 that are about a 3-to-1 ratio. Right? Because a 75-25 split of chlorine 35 and chlorine 37. So this M peak again is going to come from that propyl, that 2-chloropropane that has the most abundant chlorine 35 isotope, and then this M plus 2 peak at 80 comes from that 25% or so that has the chlorine 37. Okay. And so what we can see in these cases is that, again, so this is the molecular ion, that's the weight of the molecule. If from either one of these things we split off and actually lose a chlorine, we get 43 mass units, which corresponds to a carbocation, right? But one thing that you can see is that we also have this fragment here, which is a little bit weird, right? Because these two fragments, if you look carefully at them, they still exist in a pair in about a 3-to-1 ratio. And so what I can conclude from that is that this fragment still has chlorine. Okay, so we can learn a little bit about the structure just by looking carefully at the fragment. So I see only one major peak up here at the base peak at 43, so I know I've lost the chlorine in that case. That corresponds to a loss of 35 mass units. Also, if I look at these two down here, I can tell right away that I still have chlorine in there. So what does this fragment look like? That fragment looks like this, and we'll talk a little bit about how you might come up with that fragment in just a second. So that fragment is what is this piece right here, and so we'll talk about where I got that in just a second. Okay, so this brings us to sort of a quick discussion of fragmentation patterns with more complex molecules. And so we're going to use the halogens real quickly to look at fragmentation patterns to sort of put this system to bed. Okay, so what we'll do is we'll take a look at this particular mass spectrum in just a second. So let me switch over to a blank piece of paper on here so that we can take a look at fragmentation patterns. So we're not going to spend a lot of time on fragmentation patterns. You can take an entire class on this if you want in terms of learning how to analyze mass specs. It's sort of way beyond the scope of what we need to worry about here. So so we're just going to talk about two common fragmentation patterns. Okay, the first one is what's called a heterolytic cleavage. Okay, and so these actually turn out to be pretty easy to do in cases where you have a heteroatom that has some lone pair of electrons on it. So that's what we'll think about. So The point is, if we have lone pair electrons on a molecule, those are going to be the easiest ones to eject when we hit with the electron beam. And so the convenience of that is that once we do that experiment, I actually know exactly where my radical cation exists. Okay. So I would get a mass to charge M plus radical cation, and I can pinpoint exactly where we lost an electron. We're always going to lose one of those lone pair electrons from the heteroatom initially. So that's the molecular ion. A heterolytic cleavage is going to be where I break a bond right next to that. So I'm going to break this bond right here that we're highlighting. I'll break a bond right next to that radical cation in such a way that we give the electrons in that covalent bond to the radical cation to get rid of that positive charge. So I'm going to dump these electrons from the carbon bonded to the heteroatom onto the heteroatom. And so that's going to break the bonds, and this is what I'll get. I'll get a carbocation at that position where I just broke that bond, plus I will get a neutral X species. And so in this case, this would be a fragment ion that I can detect. And this would be a neutral that I don't detect. Okay, so that's one type of cleavage that we can see. In generic sense, the other type of cleavage that we'll encounter is what's known as an alpha cleavage. Okay, so we're going to start out the same way. In a generic sense, we'll have a neutral compound that has a heteroatom. We'll hit it with our electron beam. We will generate a radical cation as the species that gives rise to the molecular ion. So that's where we will learn about the molecular weight of the compound. But then we can actually cleave this system at what would be called the alpha beta carbon juncture. So we're actually, the bond we're going to end up cleaving is this one that we've highlighted in yellow. And so we're going to move some electrons using single electron processes now. And so here's how the arrows will look to cleave this system. We'll take that single electron from the radical cation, we'll dump it in to form a new bond, and we'll form a carbon X double bond by stealing one electron from that highlighted bond, and we'll move the remaining electron over here onto that carbon. And so if you're a little bit careful about what you're looking at, what these things are doing is we're actually rupturing this bond that's highlighted in yellow, and that's where we're getting the fragment pieces. So if you follow those electrons, what I'm going to get on the right hand side is I'll get an X species where I've formed a new bond at that carbon. These electrons are still here. That positive charge, importantly, is still here. And then the piece that I've got on the other side as the fragment is a carbon-based radical. Okay, and so this now containing the halogen is the F plus species that we can detect. And here is a fragment that's neutral that is undetected. Okay, so those two types of fragmentation patterns are very common for species that have a heteroatom that have lone pair electrons, because when those are present, we can pinpoint exactly where that single electron was ejected to make the molecular ion, and that lets us go through and figure out fragmentation patterns. All right, so let's look back at this 2-chloropropane that we were looking at just a minute ago. Okay, and we'll swing back and look at that. So let's look at just a few examples. So this is one that we were looking at on we had an example of the mass spectrum of this compound. If I take that material and I hit it with a high energy electron beam, I can eject a single lone pair electron from that chlorine. That's going to give me a radical cation. That's going to correspond to the M plus species and the M plus 2 species, because again we'll have an M plus at 78 mass units for the presence of chlorine 35, and then we'll also have that M plus at 80, M plus 2 at 80 EMU for the heavier isotope of chlorine. But again, there are two ways in which this material can fragment. So we can see two fragment pathways. The first will be again the heterolytic cleavage. The heterolytic cleavage will look like this. So again, we've got the radical cation here. Heterolytic cleavage will just be breaking that chlorine bond, the carbon-chlorine bond, taking the electrons away from carbon and giving them to chlorine. That heterolytic cleavage is going to give me a carbocation species plus an atom of chlorine, which is neutral. So again, this is not detected. And then what we'll see in its place is a fragment piece that's positively charged. This would be detected, and it would give us a molecular weight of about 43 mass units, right? And so that corresponds to the molecular ion having lost the chlorine, which we don't detect. We get a mass to charge ratio of 43 for that carbocation fragment, and if you look back at the spectrum, that turns out to be the base peak in the spectrum. So this is the most common fragmentation that we encounter in this particular molecule. But another way that that molecular ion could release some of its energy would be to undergo the alpha cleavage. And if it undergoes an alpha cleavage, it would look like this. So again, we'll start with that molecular ion. And the way in which we would do an alpha cleavage will be to move one of these electrons down to form a carbon-chlorine double bond, and we will steal one of the electrons in a neighboring bond to form that carbon-chlorine bond and put the remaining electron on one of those carbons. So again, the bond that I'm rupturing in this case is going to be this carbon-carbon bond, one carbon removed from the chlorine. And so if you follow those fragmentation patterns, what I will get out of that is this chlorine species that's positively charged, and then I will get out of that a methyl fragment that is uncharged. So again, that methyl fragment would not be detected. This particular alpha cleavage fragment, which contains chlorine, would be detected. Since it contains chlorine, though, we actually see a peak at 63, which corresponds again to chlorine 35 in this fragment. And we also see an M plus 2 peak at 65, which corresponds to chlorine 37 being present in that fragment. And so if you look back at that mass spectrum that we showed for this molecule, you should see these peaks corresponding both to heterolytic cleavage and also corresponding to alpha cleavage. So if we jump back quickly to that spectrum, we can see those, right? And so in this particular case, the loss of the chlorine from the molecular ion to give 43, that is the heterolytic cleavage. And then these two peaks here corresponding to this structure, that is the alpha cleavage. Okay, so just about any molecule that has a heteroatom will have these types of cleavage fragments that are available to see. Let's take one more look at another molecule. So here's an alcohol that will also have similar fragments like this. Okay, so let's take a look at this example, for instance. So if I add up all the carbons, hydrogens, and oxygens in this compound, I should see a molecular ion peak that corresponds to 102 mass units. Okay, and so then I can think of a couple of other types of cleavages that might happen, right? Because now, since I know that I have a heteroatom, I can actually look at and pinpoint exactly where those electrons sit on this molecule. So to get that molecular ion, I'm going to eject one electron from that oxygen, right? And so what I would get in that case is this as the molecular ion, but then I have ways in which this can cleave. So I could cleave off that oxygen in this way, so I can just break that oxygen off here. That would correspond to a heterolytic cleavage. Or I could break one of those bonds that are neighboring that species, so I could break a bond here, or I could break a bond here. These would correspond to alpha cleavage products. And so if you go through and do the arrows for those things, you should be able to pick out some of those fragments in the mass spectrum that you would see. So let's take a quick look at that in terms of how you would draw those out. So let's see, we got 6 carbons on this thing. So here's the compound. And so if I were to hit this molecule with a high energy electron beam, I know that my first ionization event is going to happen by ejecting one of those lone pair electrons from the oxygen. That's going to correspond to my molecular ion peak of 102 mass units. And then I can think about fragments from there. So if I think about a heterolytic cleavage, I would start with that molecular ion peak, and I'd get to a heterolytic cleavage by giving those electrons to the oxygen to get rid of that positive charge. I'll end up making this carbocation, which I would detect, and I would get out of that a hydroxyl radical, which I would not detect because it is neutral. Okay, so that's the heterolytic cleavage product. If I think about an alpha cleavage, I've got 2 pathways here for this one. So alpha cleavage 1, so this depends on which direction we move electrons, right? So here is my molecular ion. I can cleave this bond through a alpha cleavage if I move electrons in that direction. So the way I would draw that is these electrons will fold down to form an oxygen-carbon double bond, and I'll pull one electron from that carbon-carbon bond to do that, and I'll dump the remaining electron on that methyl group. So those arrows are telling me that my alpha cleavage product should look like this. So I've formed a new carbon-oxygen double bond, and I've split off a methyl radical. And so again, I would detect this alpha cleavage product. Gotta learn how to spell detect. And then I would not detect the methyl. So that's alpha cleavage number 1. I can also think about alpha cleavage 2. Alpha cleavage 2 will look like this, so I'll have the same material. Still have my molecular ion peak in the same place, but in this case, alpha cleavage 2 is going to end up cleaving this bond. So I'll get larger fragments in this case. So again, I'll dump one electron in to form a carbon-oxygen double bond. To do that, I'll steal one electron from that bond and place the next one over here. And so what I'll get out of that is this radical, which is not detected. And then I'll get this alpha cleavage product, which I would detect. Okay, so those are some of the most commonly encountered fragmentation patterns that you will see for atoms for molecules that have heteroatoms. Okay, that's all we need to know for mass spectrometry for this class. So we're going to stop here, and we'll spend some time in class on Friday doing some examples of this to hammer it home a little bit. All right, I will see you guys later.